Let me brainstorm questions that create immediate tension. The phrase, ash plume, feels visceral, could anchor it there. Why would lightning strike upward in volcanic ash? That's counterintuitive, since we expect lightning downward. The sky bleeds gray. A plume of ash punches through the stratosphere, thick as smoke. Heat radiates from the crater. Then lightning, not down but up, tearing through the choking black cloud. It cracks, a sudden white line against the gloom, not thunderstorm lightning, something else, something violent, born of fire and dust. Scientists watching the plume on video footage from Iceland's Eyjafjallajokull eruption in 2010 noticed it first. Not a random bolt, a pattern, lightning bolts shooting asterisk upwards from the densest part of the ash column. They paused the recording, rewound, watched the same sequence again. The bolts weren't seeking the ground. They were climbing asterisk through asterisk the ash. The phenomenon had been observed before, but never systematically. Now they had the evidence. The ash particles, tumbling violently in the updraft, collided. They rubbed, built charge, like ice crystals in a normal storm cloud, but driven by the volcano's power. The static built until it discharged, clean, sharp lightning within the plume itself. A dirty thunderstorm. Astronomers estimate the charge separation happens rapidly. The collision rate of ash fragments is immense during a violent eruption. The resulting lightning isn't just spectacle. It's a direct measure of the eruption's intensity and ash concentration. Studying the frequency and pattern of these bolts helps scientists monitor the eruption's scale from safety, long before the ash reaches populated areas. The storm within the storm tells its own story. You feel the heat radiating from the mountain as the first lightning strikes the ash plume. Not skyward, but deep within the churning cloud, a jagged bolt splitting the dark gray. The air crackles, smelling sharply of sulfur and burning rock. Observers on the distant ridge see the lightning not as a flash, but as a sudden, violent pulse within the storm itself, a clean white fracture against the gloom. It splits the plume at 9,000 meters, visible through the dense, gray-black cloud, leaving no doubt. This is not weather, this is fire's own thunder. Documented at Eyjafjallajokull's 2010 eruption and Taal's 2020 blast, the lightning is a constant companion of explosive events. Scientists measure the rate of discharges, up to 10 strikes per second during peak activity, directly correlating to the eruption's intensity. Each bolt maps to 300 tons of ash being lofted. This isn't spectacle, it's a real-time, electrical heartbeat of the volcano, visible from safety kilometers away. The leading explanation is collision charging. Within the eruption's furious updraft, cinder-sized ash fragments tumble violently, scraping against one another like sand in a hurricane. Billions of particles collide every second. Friction strips electrons, separating positive and negative charges. The charge builds rapidly until the air can't hold it, discharging as lightning within the plume itself. Sensors on Mount St. Helens recorded the electric field strength, spiking to 100 volts per meter during such events, confirming the process. Alternative theories suggest lightning forms when ash shatters on impact, but observed patterns contradict this. Lightning clusters in dense, sustained bursts, not isolated sparks. At Sakurajima, Japan, high-speed cameras captured lightning tracing the exact path of ash-rich updrafts, not random fragmentation points. The data aligns perfectly with the collision model, continuous, widespread discharges driven by ongoing particle collisions. The storm within the storm is a silent, precise monitor. Each lightning strike is a data point. The frequency, the voltage, the location within the plume. Scientists use this to calculate ash concentration and eruption velocity, predicting ash fall hours before it threatens cities. The lightning isn't a byproduct. It's the volcano's own electrical language, spoken in sharp, clean bolts that map its fury in real time. The storm tells its own story, written in light. The air at Sakurajima crackles before the first bolt. You feel it, a sudden static hum beneath the eruption's roar. High-speed cameras, frozen at 10,000 frames per second, capture lightning not as random flashes, but as a precise web tracing the plume's deepest, fastest updrafts. Each bolt follows the exact path where ash-rich gases churn, not where fragments strike the earth below. The pattern is too consistent, too rhythmic for random shattering. The shattering theory falls apart under this scrutiny. If lightning ignited when ash hit the ground, we'd see isolated sparks at the volcano's base, like sparks from a grinding wheel. Instead, the strikes cluster high, dense, and continuous, like a storm within a storm. At Eyjafjallajokull, the plume lit up with lightning pulses matching the eruption's exact intensity. Isolated impacts wouldn't create this synchronized, widespread discharging. The data doesn't lie. What would finally confirm it? A global sensor array, synchronized across active volcanoes, tracking lightning patterns against real-time ash density and gas flow. Current observations are fragmented, like seeing only one frame of a movie. A full dataset would show if the electrical discharge rate directly mirrors the collision frequency of ash particles within the plume itself. Without it, scientists rely on partial evidence, calculating ash concentration from strike frequency alone. This electricity isn't noise, it's a direct signal. Each lightning strike's voltage reveals the plume's momentum. The strike frequency maps its density. Air traffic controllers receive warnings hours before ash reaches airports, using this data to reroute flights. The volcano's electrical language is precise. A single bolt at 50,000 volts tells engineers the plume is moving at 100 meters per second. No guesswork. The storm within the storm speaks only in light. It doesn't scream, it maps, it predicts. Every flash is a silent, accurate measurement of the eruption's heart. The lightning isn't a symptom, it's the eruption's own electric pulse, written in fire across the sky. What other silent languages does Earth speak?